We next have an industry panel verifying on the bleeding edge of breakneck speed. The moderator is Yudhishthira Kundu, Senior Director at Intel. Just a few words about Yudhishthira. He's a Senior Director at Network and Edge Group at Intel with 22 years of experience. Prior to Intel, he has worked in Qualcomm and Transwitch. His experience spans across all domains, from conceptualization to commercialization of silicon products. Currently, he leads networking and edge products, development and delivered successfully for the networking, mobile, client, data center, IoT, as well as edge markets. He is an alumnus of Army Institute of Technology and received his bachelor's degree in electronics and telecommunication engineering. I'll hand over to Yudhishthira for introducing the panel, who will be Dennis Brophy from Siemens EDA, Pradeep Babu from Qualcomm, Sukumar Raghuram from Rivos, and Suraj Kamat from ARM. Over to you.
Thank you very much. Good morning, guys. Okay, I have my cheat sheet to start with. First of all, I think before we go to panel introduction, you people will be wondering, what is this panel all about? Verifying on the bleeding edge at breakneck speed. Yeah, even when I first heard about it, I thought some science fiction. So, yeah, okay. Is it echoing? Okay, thank you. This panel was supposed to be moderated by Mr. Shankar Hemadi, my Intel colleague and mentor. And this panel topic is brainchild of him. And unfortunately, he can't travel from US. And I have been requested to moderate on his behalf. So I'm thrilled and honored to be moderator of this panel. So as we know, right, all people are talking about, I think our keynote speakers also talk about the technology at the pace we are seeing that change is happening, right? Human race has not seen this kind of change in the technology advancement so far. AI, ML is everywhere. 5G, 6G is going to change the landscape. On top of that, computing is becoming ubiquitous. So with this change of pace in technology, we, both silicon and software product developers, also need to work at that pace so that this technology is available to end user. What does this mean? This means we have less time to verify as compared to earlier, but we have more functionality to validate it. And it's not only functionality, it's more than functionality. It's about safety, security. It's about efficiency, which include performance, bandwidth, latencies, power requirements. So that is the landscape about this panel. Now I'll start with the panel introduction. First, I'd like to invite Dennis Brophy. Dennis Brophy is a Director of Strategic Business Development at Siemens EDA. And he has reached 42 years experience in the EDA industry. So he's one of the veterans, and we are privileged to have him on this panel. Thanks, Dennis, for joining this. Next, I would like to invite Pradeep Babu. Pradeep Babu is a Principal Engineering Manager at Qualcomm with 22 years of experience. And he mainly works in automotive products. And he basically did his bachelor's in Madras University. He holds 2 patents. And he has contributed to verification community, being a judge in CDN Live. So thanks, Pradeep, to be part of the panel. Okay, next, Suraj Kamat is a distinguished engineer at ARM. Again, 19 years experience in the ARM, A/R/M category of CPUs. And he's basically handling definition and defining and improving verification methodology, as well as incubating new teams. He is also driving machine learning for verification for CPU at ARM. And our fourth panelist is, yeah, you can't see him. He's stuck in Bangalore traffic. He started at 7:30. So I asked him, okay, as a responsible engineers, as a social responsibility, please study these Bangalore traffic problems also. Other than verification, try to find solution for them. So we'll start, and as soon as Sukumar comes, by any chance, he'll join us in between. But I don't think so he'll be on time, okay? Okay, to start with, okay. So I'll start maybe with Dennis, maybe to share your experience on the current challenges we are seeing, specifically in the verification environment in your, whatever you are doing in your work today.
Sure.
Yeah.
Is my mic working? Yep. Okay, good. I think you've actually seen in some of the keynotes what's kind of going on right now, where we're attempting to advance the use and adoption of compute technology to help out solve and resolve bugs we have. But just taking a look at what the survey, I think Dave Rich pointed out, top three areas, and the one that's most pressing of late has been the integration of analog with digital. And if you get something wrong, we're going to have to do a respin of your design unless you own the fab. You may be at the mercy of going to the back of the line because you failed. So the cost of failure is not even just the traditional one of not making a market window, but it's not being able to be in line for fab production because you didn't maybe even schedule maybe a few mask set changes, what have you. And I think there's solutions that are evolving that I think we're going to begin to exploit. Chiplets are going to, I think, bear a lot of promise, where perhaps older technology will allow us to place some of the analog in a known working silicon, and yet at the same time fuse those into being coupled into an overall package, into an overall system. So I think we're experimenting with a lot of this today, but I think even the first keynote was pretty clear. The unrelenting move towards smaller and smaller geometries continues. So if 5 is being released today, we all know people are playing around with 1, 2 nanometer geometries today. So the pace that we're on at the actual edge, maybe it comes back to your point as well. And this has been an axiom for a lot of history. Most of what we see today was designed and developed in the last 10 years. I don't see punch cards anymore, Dave. I've used them. I actually went looking around my house if I kept anything from college. I have no punch cards. But I think that actually shows us that for the next 10 years, it'll be like probably the same as well. And so the big problems we're pressing that we see today, one, obviously, getting the functionality right, but one that came right out of the blue was the impact of analog and digital together. And we know that with telecommunication systems that you've pointed out, those will come in spades as these devices on the edge have to deal with a lot of this as well.
Thanks, Dennis. So basically you are saying chiplets, analog, digital, integration, those are the biggest challenge we are seeing today, right?
Yep.
So.
And I was going to mention one. I didn't think we'd hear the word correct by construction yet. It's an old term, and I was amazed to see Dave had that in his presentation. A lot of what we're trying to do with static verification up front is to get it right before we go off to use any formal or functional verification.
Dynamic verification. Yeah. Thanks, Dennis. Thanks for your perspective. Pradeep?
Hello, is my voice visible?
Yeah.
Okay. Yeah, so especially the challenges what we come across is Qualcomm is known for the mobile, and we are also entering into the multiple adjacent market segments. So mainly automotive is one of the area where I've been working on here. So some of the challenges we had was that we always talk about the functional verification, how do we converge use case verification and all. So when it comes to the safety side, so it's not only about the application what we run, the entire chip is going to be monitored in parallel. And how do we ensure that any of the safety violation happens across the chip? And do we have enough safety mechanisms to catch and prove that, right? So that's one of the major challenge we go through. And also, if you look at it, there are certain certification process, like if you're targeting for a DAS application, you go for ISO 262 safety compliance and everything. And also, we have to run the testing in the field. And basically, it means that you are running an application, you are multiplexing with the testing functionality in the chip on the field when the car is running, right? So those kind of unique challenges has come across, and a lot of innovative solutions we are looking for those areas. So those are the interesting aspects.
Yeah, it's interesting. So basically you are saying on top of safety, the in-field testing also, right?
Yes,
So
yes.
yeah, so
So
those
we
are
run
main challenges for you.
Test functionality.
So design
test
for
function-
in-field testing, right? So,
Correct.
excellent.
Yeah.
Suraj, you want to add?
Sure.
Thank you.
So designs with higher complexity, I mean, as designs continue to evolve, verification lags and needs to continuously innovate, right? So the challenge, I have multiple challenges that I'm seeing. In general, one of the key ones is how do you enable design bring up to be quick so that you are enabling everything to be, shift left, which Manish mentioned earlier. How do you enable that quickly enough so that everything you can throw all the different strategies at the design quickly enough. Second thing I see is how do we manage our automation and verification costs, because you need to keep the pace, but at the same time you have to ensure stability and quality. How do you manage that on the go and keep it all the time? Third challenge is see how do you reduce the probability of high impact corner case bugs. So these bugs, when they escape, and bugs are getting pretty complex. There's like 10 different conditions are coming together to cause that bug. You can't think of that via coverage point or via a test case or anything, right? So how do you bring down the probability of something happening like that? And the last one I see is very often we lack how a feature is going to be exactly used. Something Pradeep is highlighting on the field testing. Why do we need to do that? Because if we do a verification just on the basis of the spec, you will be covering the spec to a larger extent, yes, but there will often be something else which is out there which you can't think of, which will come out by knowing the case. So understanding how some product is going to be used and ensuring that it works in that case brings down the probability. So there are different challenges more than this, I think, in terms of safety and security. But to me, our traditional methods of verification are no longer sufficient. They're only necessary. So we need to do much more to bring in, to make verification sufficient.
Okay, thanks, Suraj. So your point is with increased complexity, reduced time, right? So traditional methods are not falling short, right? So we need to do more work there. Thanks. Thanks for sharing your perspective, folks, on the challenges you are facing in your current work. So maybe question for you, again, Dennis, to start with.
Not a problem.
Okay. So what are the main causes of SoC respin today? And what can be done to address them? Because it's become illegal to get first pass silicon working, right? So
Yeah, I obviously getting the functionality correct up front still is an issue. That you find field failure when bringing a device out, and I've watched some of our customers point back at the tools failing when they've taken devices into the field to test, because they were actually in production with devices that were failing. And the root cause of one of them was a mismatch between the processor and the memory subsystem that was supposed to go. They used an old memory subsystem with a new processor, and it only failed while in the field. You basically were on your telephone and you went from one tower to the next, and it would drop, and they couldn't figure out why. And we've gone to elaborate lengths, not just that this customer outfitted a truck and was driving around the metropolitan area near where they are, but I visited a test lab up in Canada, where they're actually, all the handset manufacturers brought them in, and they were simulating a whole city. And of course, I didn't know if I was getting radiation poisoning with all the cell towers sitting right there. But that's today's problem. And I would like to pick up a little bit on where a lot of this is going for the future. If we talk about handsets and the mobile telephony, that's one thing. But the safety, security of going into just automobiles, if you look at the life cycle of an automobile, it's not 1.5 years. You're not going to sell another 1.5 billion cars and be able to throw away the old silicon. So we also have silicon aging issues to deal with. And if the silicon doesn't age well, how does it fail so it doesn't kill anybody? And maybe just like I got with my computer. Dell, during COVID, sent me a message, they have to come out and fix my computer because the diagnostics that are being picked up indicate from all the data they've learned from device failures that my machine was set to fail. So I got a new motherboard, which also to me is the other big problem I think we need to deal with. If it's not just reliability for the silicon we're manufacturing, it's how do we gain access and share data as well. And so one of the IEEE committees I'm a member of, a lot of different market segments are bringing in to the standards setting a way of defining what it is. So Dave talked about all the cats, or all the animals you can see, or all the books in the world that Google has read. It's read them all, by the way. So they have data. But for design, the design data may be a competitive weapon between one company and another, and you don't want to share your learning because not only might we have a tool that helps you, but now you've just helped your competitor as well. And there are a lot of markets where this is actually they're overcoming a lot of this, and I don't know if the electronic design market and the EDA market are ready for that to happen yet, but I do think there needs to be some serious discussions because if we're going to be tackling the hairy problems at the edge, we can't afford not to.
Okay, thanks, Dennis. Thanks for sharing. Suraj, you want to add?
Yeah, I think, do you see something where we try to abstract out the specific aspects of which a company might not want to share versus, and use them towards standardizing? It's still a journey. It's a long journey, I feel, but yeah.
It is, and I know of one company we've worked with, we're finding bugs in their new system, tracked back to old blocks
Reuse blocks
that were not changed.
Yeah.
So how did a bug go undiscovered for 8 years, and all of a sudden you've discovered something? And that information, they have all their sim runs, they've saved all the information of what they've done, so they've got probably petabytes of information that they could feed to an AI solution as they come on, and I'm almost certain they would want to keep it for themselves and not necessarily share, especially when they're attempting to train the system with their information.
Okay, thanks, Dennis. Pradeep, you want to add something specifically?
Yeah, so in continuation of Dennis, he talks about automotive, right, the long-term cycle. So definitely it kind of breaks from the start, like the leaf level components onwards, that how do we make sure the technology components and the designs are robust enough to survive across a 15 years plus life cycle, right? Like for example, the specific case we can take, so in automotive, the ASIL compliance is mainly targeted how much fault you can cover on your design, right? So how do we guarantee that on the field the device does not fail under certain radiation conditions, right? So how do we qualify?
Got it.
These are the challenges which we have to address so that we can avoid
Yeah,
doing
got it,
spins,
Pradeep.
spins,
So
spins.
basically, you people are saying these products now going on in this mission critical
Correct.
application and lifespan is long, right? So they need to survive for that lifespan.
Yes.
And that is one another area where a lot of focus is there. That's also resulting in a lot of respins because of aging related problem, right? Or reliable under radiation conditions or other extreme environment condition product needs to work
Yes.
properly. So,
So right
okay,
now, if
yeah,
you look at
interesting.
it, I think most of the people would have heard about the edge stall testing, right? Like high temp testing. You kind of mimic the long-term cycle effect, right?
Correct.
Similarly,
Yeah.
now we are talking about the radiation testing, like your
Correct, correct.
leaf level tech lip components undergo radiation testing. Does it really survive across?
Yeah,
Right?
this survive and it needs to fail safely because
Yeah. Yeah.
human life is at cost. Technology is so pervasive now, right?
Correct.
Yeah.
So
Thanks.
another part I just want to add is like now we have options of multiple foundries and everything, right? So when you make a design or SoC, like how you make it as technology independent, and we are keep on shifting to a newer tech node. At the same time, there are multiple foundry
This is
options.
age-old problem, Pradeep, we are
Yes.
discussing.
Yes.
But I think that's where clearly some of the fabs have gotten together, TSMC, Intel, and the like, to talk about chiplets in this area, so
Correct,
that
correct.
at the boundary, silicon can be brought together in some fashion, whether through an interposer or other techniques. And I think that might be something that addresses it, because again, I don't think they had a vested interest, any of these companies, but to work with themselves, but to see Samsung, TSMC, Intel willing to collaborate on a specification and definition of this, I think gives us great hope.
That's
True, Dennis. And just to add, right, because we have seen all these supply constraints, specifically fab side, and we know one fab will not be good enough, right? And so it's a full ecosystem. We need to come together, and based upon where our requirements are met, we can move seamlessly to any fab. I think that's a great initiative, and that standardization definitely is one step in that direction. Yeah.
Yeah.
Thank you. So Suraj, maybe for you. So how should automation, cloud capabilities, machine learning be utilized towards helping at this journey we are facing where designs are becoming so complex, right? And we have to validate not only basic functionalities, so many other aspects which we just discussed about, right?
Sure. Definitely, I think we'll have to, you can look at all of them together, all of them separate, but I would say let's look at them separate, right? So automation has always been a key enabler or efficiency and helps us keep the pace. So it is there, and it has its plus and minuses in terms of how much do you innovate in automation. You need to do needful automation, needful innovation, but not needless innovation. I think as engineers, we always want to change things, make them better. But at the same time, you need to understand, anytime you change, there is a cost of making it stable for the longer run. So when you look at automation, I would look at it as something which is specialized. We need specialized skills towards it. We have seen verification engineers do automation work, but I would say as we grow and we scale up, it is best managed by somebody who is skilled DevOps people and not traditional verification, but somebody who understands the IP life cycle as we take along. So automation definitely is key. We have to use it. We have to make best use of it. And it has an impact on CI frameworks, your regression efficiencies, how you root cause some things. So all of the productivity improvements are on the backbone of automation. Cloud, if you take, cloud is there in production everywhere and has multiple use cases. It gives you burst capabilities where you suddenly need to accelerate, or when you get things coming back to you, you want to verify them quickly and send it back. And so it allows you to do that quick at a burst capability in quick time. So cloud capabilities are helping us stabilize things which would otherwise take long to stabilize by looking at an opportune moment. It is there allowing us to scale. But I think traditional verification flows, when they're interfacing with different cloud vendors, they still need to do a fair amount of jugglery at the back end. And that is something which will help improve. On machine learning, I think in the morning session, definitely all the particular aspects were brought out very clearly. It is there, everybody wants to do it, and we are seeing it, point solutions having good impact, but it's not there everywhere yet. And a big problem is data. And definitely we need people who understand data as data very well, understand data engineering, not just pure verification. Verification perspectives are required as to where to apply, and it is a field which will grow, definitely, and everybody wants to stay invested, as we have seen examples in image and speech and other areas where it has been largely successful. So with machine learning, I feel it is up to us as to how do we manage to apply it and make use of it for the critical problems that we see.
Yeah. Hey, thanks. So Dennis, I think with this cloud specifically, right? So the security aspect, what data we want to send outside is a critical component. Do you want to add something on that?
Well, I'm probably a big believer in it, and I will agree with you. It's not where it ought to be for everything, all the time, everywhere. And it has found some good promise early on with burst capability and the like. But I've also seen some exploration of what compute technology actually exists at the cloud or on at the sites where the the hyperscalers are. Our Formal 2 as one shows extremely good performance with the Graviton on AWS, where even getting access to that device, if you want to have your own installation on your own site, is going to be almost near impossible to do because the production of that is captive to filling out AWS. I looked at some guys from Berkeley who used instantiations of Xilinx devices. They're also, for a college student, kind of hard to come by, but they prototyped an entire cloud infrastructure based on their chip that they were doing, prototyped in the Xilinx FPGA. And I think this is where we will get into a point where the algorithms that we're working on today that might be authored in C++, they may actually end up as custom hardware implementation as well. And I think this is where the cloud is going to allow us to explore even greater productivity boost by being able to do that. So this is all kind of new for us. The next thing then is how do we make it accessible and available to everyone as well. And those business issues have to be worked out because I think you mentioned some people are going to be very cautious about allowing their own IP or their RTL to migrate out of their environment and be handled somewhere else. But I think there'll come a day of reckoning where those companies, or maybe startups, they may not care as much about that, will begin to use it, and they'll get leapfrog of productivity based on what the other companies that are more entrenched. And there's a lot of there's a lot of scenarios that we can explore on the business side of stuff, the innovator's dilemma, where it's good enough for us right now, somebody else takes a path and they bypass. So I'm actually looking forward to the bypassing that's going to be happening.
Thanks, Dennis. Thanks for sharing it. So maybe Pradeep for you.
Okay.
So this is mainly related to safety, right? So and you are currently working there. So we know, right? So safety requirements are very stringent, specifically in ADAS and other kinds of applications where systems are going, because those are mission critical and time-bound applications. So how do we basically, with this safety being one of the dominant factor, so what we should be doing so that along with safe functional and power and other aspects, so that safety validation can be the inherent part of our validation or verification approach. What can be done on that side?
Yeah, that's a good question. So just to go in, before going to the verification, I just want to give a little bit context on why we are talking more about safety. And so when we look at it, all the cars, like maybe 15 years back, the safety was just a requirement to assist the driver. And we talk about the front camera and the back camera associated with the car. kind of helps the driver to manage it, right? So how the architecture was evolved that time for us was like it was more of a distributed network where wherever you have these kind of safety related solutions where there will be a closely associated processor or a chip microcontroller which manages that, and it all connected through either the car area network.
So you are saying distributed network within car system?
Within the cars,
Okay.
within the cars itself. So you have a CAN network where all
CAN
these
network.
connected. So that was okay to some point of time. So when we moved towards the autonomous car, like in the automotive, we call it as level 1 to level 5 of evolution of the automotive requirements. So when you are looking at autonomous car, no more we are in the legacy of running with a small microcontroller and verify standalone and put it on a network. So now we are going to make chips which is comparable to the whatever is there in the compute or mobile space, the biggest chips what we have, along with functional safety. That's a key differentiator that every block we design, like you have n number of cameras, radar systems, everything, right? So everything requires a high-end camera resolutions, display, AI engine which can process those images and take decisions, right? So these IPs are going as complex as any other field. Along with that, these IPs are getting developed with the functional safety compliance. So now comes to the verification challenge, right? So how do we take care? Like how do we ensure that, like example, if you have a GPU with the safety features added in it, how do you ensure the GPU, IPU does not fail in the field? And any of the safety violation happens, how does it, your hardware mechanism is able to catch it, right? So these are the unique challenges which comes up on the safety side. And if you look at application point of view, we always look at the use case which we run, and the safety function, it's not going to participate in any of your use case. It's going to sit in parallel thread and continue to monitor your use case and see that any component is
like
going
snooping,
to fail.
right? So
Snooping,
parallel.
right?
Yeah.
So that's kind of put a different challenge, how you are not implementing a safety monitoring function which is not interfering with your end use case and application, and make sure your KPI met at the same time the safety is guaranteed, right? So that's kind of puts a unique verification challenge. So coming to the exact metrics, so one is the safety, all the function verification metrics. How do we verify and guarantee? That's a kind of functional verification. And there is a more stress on the negative scenarios, like you inject error and then see the response of your system, starting from the leaf level block all the way to your system use case, right? How do we ensure that it works? And another factor we talk about functional coverage or code coverage in the regular verification. So there is a concept here called diagnostic coverage. So this is a coverage metrics is demanded by ISO 2622 standards. The amount of percentage you meet the coverage there, it gives you the ASIL B, C or D certification.
Grading. Okay.
So let's say you hit your fault coverage using the diagnostic coverage as 90%, then you are in ASIL B, you are 99, you are ASIL D, right? So when you sell your product, you will be, you will be looking at whether I'm selling my product for ASIL B or ASIL D. It all depends on your diagnostic coverage. So, and it's a parallel activity which we have to do on top of your functional verification. So you do the functional verification, you take your IP under the fault injection verification, grade your IP that 90% of my logic or 99% of my logic, if it has a failure in the field, I have a mechanism to catch it, right? So that's a unique challenge, and it's a long cycle, and we talk about the verification cycle optimization. So this fault coverage, diagnostic coverage takes like 4-5x amount of the regular verification cycle. So the unique challenge for us, how to optimize that and still meet the time to market.
Time to market. Right?
Yeah. So yeah, these are some of the interesting factors.
And you want to add something on? Basically, yeah, we know failure is going to happen, right? Only we can reduce the probability of failure, right?
Correct.
So still failure happens. These devices need to be fails gracefully,
Yes.
so that it does not create some catastrophic events, right?
Correct.
So maybe something you want to add on that side?
Yeah, so definitely, see, failures actually we see as two factors. One is the permanent fault. So once it happens, the the cell or a flop is being stuck. That's one kind of scenario. Other one is that external ionized event kind of hits your design, and momentarily the flop or a cell state has been altered, which can lead to a failure, right? So there are two broad categories we have. So what are the testing mechanisms we generally use at like fabrication stage on the silicon, that stuck at testing? So in automotive case, we kind of support that in field. Like when you're running an application, you have a small window where you don't have application payload to process. You run your self-testing on those blocks and see that there any stuck-at fault happen in the life cycle of your product, right? So that's one of the metrics we have.
Okay.
And so basically like the software runs and the hardware runs, and you kind of multiplex testing versus application. That's one we...
So basically both software and hardware, right? There is a periodic in-field testing.
Yes.
Okay.
So that's one of the major area which we cover on. And also we talked about the test shape of the radiation testing, right? How much you can qualify your tech lab cells. So basically all this number calculated based on a leaf level cell fit rate. So fit rate is one factor, failure in time, it's a unit. So how do you characterize each of those device in the test chip, and when you make a product does not fail on the field? So these are some of the
Thanks,
areas.
Pradeep. So what I'm taking away from this, like security, right? It needs to start from leaf level.
Yes.
It should be a mindset. Same way safety falls in same category, right? So each and every component to when designing, architecting, need to have safety in mind.
Yes. Every block, when you define a functional feature, if it fails, what is your safety mechanism?
Safety fallback mechanism.
Yes.
Excellent. Thank you.
Hello? Yeah. So I would like to say safety is very well evolved. I think over the years, its journey has been in making it more definitive of what we should do or what we should target for. Security, on the other hand, it's still anybody's game as to how much we should do. I mean, you can put 10 security guards at a building or 100 security guards at a building. Depends on what you're protecting and what is the impact of the loss. And so with security, we are more looking towards that stuff does not, whatever has been known, whatever vulnerabilities are known, do not exist in your product. Plus, you evaluate your design features, new design features for new vulnerabilities, but that's always a game which you may get success, you may not get success. There could be somebody in the universities or hacker who would come up with a technique, and you need to continuously adapt. But at least we can give our customers the confidence that anything existing is not there, and we have sufficiently tried for something new. One thing which we do consciously is for any new design feature, we take a lot of pain to evaluate that whether this will lead to a security violation on the field. So security is still evolving, I would say. Safety is much more evolved and has a very good standard.
Yeah. You want to?
That's true.
Okay. Thanks, Suraj, for adding. Okay. So now maybe we are all talking about chiplet-based verification, right? Because chiplet is the next move, and with the increasing complexity of the design complexity, heterogeneous compute availability, different GPUs, CPUs, different fabs availability, right? So it's I think the future, right? So in industry already many companies are starting using it. Intel is doing, AMD is doing. So what is your basically take on the chiplet, right? So what benefits it creates, what verification challenges it creates? Maybe Pradeep, you can.
Yeah, I can add on the chiplet.
And specifically from automotive industry, right? So
yeah. So one topic on the auto we have not discussed in the previous discussion. So when you talk about safety, there is a redundancy concept also we built in.
Yeah.
Like for example, the simpler example, everybody knows what processor, we have a redundant core. So there's a lockstep CPU which runs, the same application runs on both the cores. If any one of the thread deviates, we report a safety violation. So that's okay from the software, from the CPU point of view. When you take to the ASIL-D kind of applications, where when you want to run the end-to-end application, and you will be looking for a lot of redundancy in the system. So chiplet is one of the way we can look at it, like you're running an application, and if you have a chiplet kind of structure, you have more flexibility to run the application on a parallel thread, and then make sure that the safety criteria are being met. So that's one of the area we really see. That means you are able to run your application across the die, and still you are able to converge and monitoring the safety. That's one area. And also, if you look at it, the major challenge from verification I see is the coherency between the chiplets. Like for example, in any processor which sends the traffic, so how do you go across the die and snoop the cache on the other cores and try to meet the KPIs, right? That's another challenge we look at it. One more point is safety means like whenever there is a failure happens, there is stipulated time where you need to react for it. So before it goes into a catastrophic event, right? So when you talk about one core which is failed in another chiplet, and it has to communicate to the central control safety unit that there is a failure I've seen, and that unit have to take an action to take the car into a safer state, right? So these complexity will expand significantly when you talk about chiplet. Chiplet is not an option, so we have to go for the chiplet because of the increasing demand on automation with more cameras, more displays.
Basically, Pradeep, you are saying there are benefits like you said, redundancy,
Yes.
easy to implement, and I think Dennis added some time back, there is a lot of efforts going on standardization of the interface across chiplets. So that's, I think, easing out a life bit, and that's the future.
Yeah.
But it creates lots of other problems which we need to address, like coherency, in time response, and we individually qualify silicons today, but now we need to start qualifying as a product.
Correct, correct.
Good.
So these
Dennis,
are the challenges.
yeah, thank you. Dennis, you want to add anything?
On the chiplet front, I think as we look at it, the verification issues, much like you might see with the different parts or blocks that you're putting together today, PCIe as a way of communicating. We're going to have with UCIe a standard that kind of sets the base for that, for an understanding, common understanding. And but we also will be moving into an era where we'll be evolving our compute memory structure. So the memory will be close to compute. The AI, ML hardware is pushing that to happen. So we have new sets of standards just to deal with memory as well. And the resiliency that we used to have with memory, or the error correction, stuff like that, that we could overcome problems with that, we may have to also begin to invent more things in this area as well as these new memory protocols come online.
Yeah, this is interesting, definitely. Thanks, Dennis. Okay, maybe Suraj, for you. Basically, this is mainly related to, we know today UVM is one of the main things. We are talking about AI, ML and other things. But what next in industry? We know we talked about problems, right? So the scale of validation, how it is increasing and time is shrinking. So what next?
What comes next?
Yeah.
I think there was a blank on Dave's presentation saying that maybe there is something that will happen next. But I'll tell you, within Accelera, we are working on a portable stimulus standard. And this one is to help reduce the dependence or the overuse of the constraint solvers. That there are going to be ways or methods which you'll be able to compute or generate stimulus that'll be much like doing that. Let's say you do your first run on the cloud and it takes weeks. You can go through and sort out the different stimulus sets that added to coverage, throw the others away. And so we're looking at making advances that are going to have a positive impact there. The other thing that probably the third most pressing issue on SoCs today is actually the management of power. And so that's another area that's added quite a bit of complexity, especially turning off, turning on different power domains. And if you don't get that right, you may not bring the chip back up or that block appropriately. And so there's a lot of work on the standard side that Accelera has been promoting in the IEEE area as well. So on the, let's say the next 2030, I think that was your prediction, Dave, we'll have a new standard for language. I think that is a discussion we would like to have with everybody and learn from what we could do better, what something would look like, and also engage with the language specialist as well. Because we did some things that built on success, much like the SoCs build on past designs to build your SoC with success. But every now and then, maybe you take a step back and redo. But if we redo it, will everybody be willing to change? And I got to tell you, my bet is very few will want to.
Definitely.
I think changing definitely is difficult. From our own experiences internally, we have a test bench which is having UVM, C, and Python in one test bench.
Wow.
The verification engineer needs to learn or be at least have a certain level of expertise in all of them. So definitely, change is going to be hard and difficult to accept and move on, unless it brings a big head start and you've got a gap between product life cycles where you push for making a decisive change.
And I've watched this with Berkeley and Chisel and RISC-V, but what was the first thing that the commercial companies told these people? Can you give us an implementation in System Verilog? So they went back to what industry was using, which is maybe really going backwards, not looking at how they actually advance the use and adoption of Chisel.
Yeah, so you are saying cost of change is not small and everyone will not be interested. It will take time, but trend is going there.
Well, we may all be dead. I don't know, if it takes 50 years for change to happen,
Okay.
We're moving much faster with what we're doing to build devices than that.
Okay, so maybe in interest of time, I think so far we are in good discussion. Maybe we can take one question from audience. Anyone have any question?
Check.
Yeah, you can come on stage also, man. That's okay.
That's okay. It was a great panel discussion, Pradeep, but I have a question to you specifically. You did mention that safety verification, the FUSA verification, takes around 4 to 5x of time. I was just wondering, what do you think we have in store from the EDA side to address this challenge? Already functional verification is taking away whatever we have. We saw 80%, so it's always it's a challenging thing. Functional verification, we have fault injection, we have ACLD where we have DC which is so high, SPFM we have to target, there is permanent fault, transient faults, 100 things are coming up. So what do you think we should have, or what do you think is already in the market, and what should EDA partners can do to help the companies such as us who are interested in the safety verification? Thanks.
Yeah, that's a great question.
Thank you, man.
Yeah.
Maybe you can speak out your name and which company you represent, man.
Analog devices, so I'm Yudhishthira here.
Okay.
Yeah, so definitely the answer from my end is that, for example, the fault coverage what we talked about, right? So that takes really long time on the simulation to convert. So from EDA side, we're definitely looking for a way to optimize those effort what engineering spending as of today. Like for example, the fault coverage, can it be a hybrid model where formal plays a role? And once you identify a certain cone of functionality where we have a fault graded already done, how does that can be formally mapped to other areas so that we don't need to prove everything through the simulation technique as of today, right? That's something EDA team can really help us to come up with a hybrid solution, how to hit the diagnostic coverage in a faster way. So that's definitely one area. And when it comes to the safety verification, it's all about the non-mission mode or application verification. So it's more about the boundary condition, error injections and all, right? What EDA tools can help us to find those nodes smartly and then try to do those verifications. So as of today, it's all depends on the engineering strategies, planning what we make, but there is no good solutions available in the market.
Yeah, or
These
maybe
are the
local
two areas.
scripting. Yeah. Maybe you people can talk offline, more discussion.
And that was my observation as well. That's why I was trying to learn from Pradeep, like if there is something already that we are not using, or probably that's something we can give a head start to, or a kind of input to EDA companies to look in that space where they can help us develop a solution. Yeah, thanks.
So we are working with the like EDA team to get those some of the features implemented, but it is in very initial phase, I would say.
Hey, thanks, man. Thanks for your question. I think we are time constrained, and Pradeep is looking at me, okay, again and again. So this is, by the way, very vast topic. We just scratched the surface, right? So just high level. We can't discuss in just 1 hour panel. But thanks to panelists for wonderful inputs, very brilliant, some of the brilliant ideas also shared, some new perspectives. And thanks for joining us. And we miss Sukumar. Thanks to again Bangalore traffic. And with this, I think we'll end the panel discussion. I'll thank all the organizers, Shreya, Pradeep, Kamal, Ashok is not there attending wedding, and everyone in the background. And thanks again, Pradeep, Suraj, and Dennis. Thanks to you there.
Thank you so much. I just call upon
Thank
Karthi
you. Nice. Thank
to
you.
give out
Thank you, Dennis. Nice.
a few plaques to first Yudhishthira and then to the panelists too.
Yeah.